Can everybody hear me? All right, let's get going on this Friday. I apologize, there's no music again. I enjoy music, but I'll make sure that this is all fixed next time. But it was even modern, too. Like, this new XX song is quite good, so highly recommended. Came out last week. Okay, so let's get started. Let's get started by doing a little bit of review from last time. So here are a few questions. So if you take anything away from last lecture, I think like the next two slides would be you should be able to answer the following two questions. So last time we motivated the entire course, the reason why you're here in some sense, by the statement that single instruction stream performance has been only improving very slowly over the last last decade, or more than a decade now. So I have two questions for you. First of all, what do I mean when I say single instruction stream performance? It's a little bit of slang, a little bit of jargon there. Let's make sure we're understanding the terminology. Yeah, what does that mean?
The performance of a processor that has that
Okay, it's on the right track, but I would say that we did say last time that out-of-order execution was a trick used by processors to improve a single instruction stream performance. So I agree with parts of that. So I want to go back to my question of what do I even mean when I say a single instruction stream? So you said that a sequential set of instructions, yeah? Well, an instruction stream or a program, like we said last time, is just a to-do list. It's a list of instructions, and presumably the order in that to-do list matters, right? Like if you got your favorite recipe and started cooking and you did all the steps that they told you to do, but you did them in the opposite order, you would probably not be particularly excited about the outcome, right? So when we see a sequence of instructions, it kind of only makes sense to interpret them, that the semantics of that are that whoever's responsible for executing that program, whether it be a simulator or a processor or an abacus or whatever, will execute them in an order that at least gets the same result as if they were done in the order that they appear, which is what you were alluding to in your sequential set of instructions. Okay, so if I say an instruction stream, I mean here's a sequence of logic that has to happen one after each other. Now why, let's go back to point one, why has the ability of a processor to run that sequence of instructions faster not been getting much better over the last couple of years? Yeah? I would say increase the clock rate, decrease the period between the two. Yeah. So first of all, we should say, well, what were our tricks for making that instruction stream run faster? So what is one of the tricks? So we could execute them completely in serial order, but just increase the rate at which we were getting every one of the steps done. Good, so that's one trick. What is another trick that we talked about last time? Yeah. So we said that the processor could say, hey, wait a minute here. I know you said that here's a sequence of instructions, but I'm smart enough to figure out when a few of those instructions can be done in parallel. So there was parallelism. One of our tricks was parallelism, except it was the hardware architects, our friends over in ECE or our friends over at Intel were figuring out clever ways to look at that sequence of instructions, as you suggested, and begin to do multiple of them at the same time. So those are two good tricks, and those were two of the major tricks that we talked about. Some other tricks you've talked about in like 2.13, like we can throw caches and other things at the processor to enable to make certain instructions run faster, like a memory access or something like that. So what was the problem with, why couldn't we just go back to that well of increasing the clock frequency? It's one of the, yeah. Because we're starting to get in a very inefficient operating regime where the cost of running a little bit faster is an extreme amount of power. And that cost was starting to become untenable, or at least not worth the extra performance that it was providing. And then what was the reason why we started running into a wall and not being able to pull this trick off of hey, let's be really clever and figure out all the stuff that can be done in parallel. Let's do that for the software. Yeah. There just wasn't enough parallelism there, right? If you wrote a sequence of instructions as a programmer, and you kind of were thinking, okay, I want to just define this sequence. You do this, and then you do this, and you do this. It's not surprising that there's dependencies there, and that the amount of parallelism to find is just not there, or you have to work so hard to find that parallelism, like look over the entire instruction sequence of the program, that you spend a lot more time or energy actually analyzing the program than actually executing the instructions. So those were you know, that's what motivated the parallelism with. And then so the question, on a different note, is last time we wrote some parallel programs. We wrote some parallel programs. We acted out some parallel programs. And we talked about this notion of speed up, meaning if we had 2 people or 4 people, well, ideally we should run twice or 4 times faster. But in none of the cases were we able to achieve that. And so what were some of the problems that we encountered in trying to parallelize some programs, which were adding up a bunch of numbers? Yeah. Poor scheduling. What do you mean by poor scheduling? Poor scheduling is sort of it's a very high-level description of what happened, but concretely, what do you mean by poor scheduling? I gave Peter too many sheets of paper, and what problem did that cause? Because that fundamentally doesn't seem like a problem to me. Maybe Peter likes paper. I gave him too much work compared to the other people. Became the bottleneck. So he took more time than everybody else, but there's one little detail you left out. Well, yeah, go ahead and finish it. Well, everybody else wasn't doing anything when he was along pole, right? So if I would have created a situation where as long as all of my processors are doing something all the time, in some sense, without changing the program itself, I can't do any better than that, because everybody's always working. So the problem of the uneven work distribution, the poor scheduling, was that different workers got different amounts of work, and because different workers got different amounts of work, there was some period of time where some of my workers were not doing anything. And therefore, that's exactly why I didn't get the perfect speed up. Okay. Were there so many other? So one problem was definitely workload imbalance. What were other problems that we addressed? Yeah. So we had 2 sub-problems that we solved well, and then we had to merge those results, and there were kind of 2 aspects of merging the results. And you guys, there were a lot of comments on this on the bulletin board. Is one of the aspects is, well, the information had to be communicated. So in this parallel system, we had this additional cost. We actually had additional work to do, which was to transport information from one side of the classroom to the other, or from one machine to the other. And then there was also some extra additional work that some people pointed out on the website, too. So there's a communication cost. And some folks really said that, you know what, I don't like to think about this other aspect as communication. There's something else that we had to do in these parallel programs. Yes? Okay, so the location of the 2 people really determined what their communication cost was. Right? So if I put one machine in San Francisco and one machine here in Pittsburgh, well, the communication costs are certainly going to be higher than if they're connected by a PCIe bus in the same machine. Right? Yeah, agreed? Yeah, so some people noted that there was actually this additional work, which was actually the synchronization or the merging of the results. So sometimes the act of partitioning a program into different pieces requires you to just fundamentally do more work than if you didn't have to partition it at all. So good, okay. So any other questions from last time, actually? Yes? We did not. We kind of really were only talking about doing math on data that was right there in front of the processor. And that will come up today. That's a good question. Okay. So there's one other thing I want to talk about from last time. Because this, we didn't really realize how much this sort of confused some folks last year. So I wanted to put an extra slide on this. So we talked about an instruction sequence. And here, to make it a little bit clearer, I didn't write assembly code. I just wrote a sequence of instructions. And if you do the math, like I'm telling you what the answer and the result should be here. Hopefully, I didn't mess this up. And so, if you were a processor architect, or you were a processor, and you wanted to run this thing as fast as possible, you could try and run one of these, every row as quickly as possible, or you could try and find some parallelism. So my first question, is there some parallelism in this instruction sequence? Yes, where is the parallelism? 1, 2, 3, 4, and 5. Yeah, 3, 4, and 5 can be run in parallel. Agreed. And I think there might be some more I've forgotten now. I made this slide last night. Yeah, there is. There's a little bit more in there. In fact, let me go ahead and visualize it for you. Here what I did is I took down I basically drew a graph, the dependency graph, and I drew a node for every line of the instruction sequence. And I just drew dependencies between all of these instructions. Right? So you were right, 2, 4, and 5 were independent, right? 2, because 3 depends on 2. So 2, 3, and 4 were not independent. I don't know, maybe I heard you wrong, but you said it correctly.
He's right.
Yeah, okay. Yeah.
3, 4, 5 are also.
3, 4, 5 are also independent, yes. 3, 4, right, yeah, actually that's true. Okay, good. So this is the dependency graph of this program. Now, if you are a processor, you can execute this program in any order that you would like, provided that you respect the dependencies. The processor cannot execute instruction 2 after it executes 3 or 6. So this program has a little bit of ILP on it. At some point, it has ILP 3. I think in other points, it has ILP 2. In other points, it actually has no ILP. So when we say executing things out of order, we are saying we are executing things in some order that respects the dependency graph of the program. Not necessarily inspects the vertical order of instructions in the binary of the program text. Yes? Now, instruction level parallelism. So we introduced that last time as saying, look, if we take a look at a sequence of instructions, even though the meaning of that instruction sequence, if I explained it to you what it means, if you look at the code, you're just going to sit there and think, okay, the processor does this, and then it does this, and then it does this. It turns out that some of those operations are independent, but do not depend on the previous one specifically. And so it emits the opportunity to correctly execute this program in perhaps a slightly different order than the way it was printed on the slide. And that is what an out-of-order processor that is trying to exploit the property of a program, which we refer to as instruction-level parallelism, to run this single instruction stream faster. And that's the type of optimizations that we talked about last time. And that's why, or one of the reasons why, Intel processors are very sophisticated and do a really good job executing instruction streams, because they find all of this independent work and exploit it for you without you changing your program. Okay, so any questions about this? Because I want you to keep this in mind compared to the techniques that we are about to discuss. Yes? Same thing, yep. Now, a modern Intel processor with a lot of area and a lot of power to burn can spend more of that area and power to try and find every opportunity that's possible to fill its particular processing units. A mobile processor probably will not work as hard to find that parallelism because it doesn't want to take the overhead of figuring out all these dependencies as much. You know, to a gross approximation, that's one big difference. And in the limit, the processor doesn't do anything for you, and you have to tell the processor exactly this. Okay, so today we're going to talk a little bit about computer architecture. And the fundamental concepts in today's lecture are the fundamental concepts that you will be really tested on assignment 1. And basically, this is the lecture that's the gateway to the rest of the class. Because if you don't know how a modern machine works, you will not be able to understand why your code is performing the way it does. So this is one of the most important lectures in the class. Okay, so let's get started. So I'd like to have a running example for the lecture, and the running example that I like to use is this simple program. It's a sequential program it uses a Taylor expansion to compute the sign, sort of what you might have seen in numerical methods class. It's an approximation to computing the sign of a number. Right? So I called my C function sin x. It takes as input an array of numbers, the vector x. It will compute, it'll loop over all of those numbers, and for every one of them, it will compute the approximation, expand the Taylor series out to terms, and then store the result, sine x. Sine of xy gets stored into result I. So I want everybody to take a second to make sure you kind of understand the code on the screen. So it's basically saying for every input element of the array, we're going to iterate number of terms times to compute the approximation of sine of the input, and we're going to store the output in the output vector. Okay, so nod if you're following the C code. Everybody's following the C code? Okay. So now we're going to compile our program. And if I gave this C program to GCC, like you did in 213, 513, what is the output of GCC? So what does a compiler do? Last time we said, what does a processor do? A processor runs sequences of instructions. What does a compiler do? The input to the compiler is a C program in this case. The output of a compiler is what? Well, let me go to somebody. I didn't understand. Somebody give me what is the output of a compiler? Somebody help me out here. I'm going to go, yes. It is a sequence of instructions. And in fact, I'm trying to give you a pseudo-coded sequence of instructions over here. And so what I decided to do is I'm showing you the sequence of instructions for the body of the loop. So we're going to carry out this sequence of instructions given an input element, xi, and notice that my first instruction in the instruction sequence is load from the address xi, and the last instruction in the instruction sequence is store the result into this address, which might correspond to result sub I. So I want you to just think about the instruction sequence for the body of the loop for now. Okay. And now I want to introduce the simplest notion of a processor that I can introduce. So we have the world's simplest processor, and it has 3 components. And throughout the rest of the class, I'm going to use this color scheme for all these components. So for those of you who have taken a real architecture class, I apologize. But for those of you that don't plan to take a real architecture class, this might be helpful. So what does a processor do? A processor will take a look at an instruction. It will load that instruction from memory. It will figure out what the instruction means, right? Like it has to decode the actual bits of the instruction. So it has to take a look at, is this an add? Is this a multiply? Is this a load from memory? Then we'll have a component of the processor that actually carries out that task. So if we're adding 2 registers, well, I'm going to have an ALU, an arithmetic unit, that will actually carry out that addition. And then we're going to store the result in the execution context, which might be a set of registers, for example. So, and what a processor does is it has its program counter, and at every clock tick, we can just simplify it for now. Every single clock, it's going to load and decode some instruction, figure out what to do, and then store the result in the register file, in a register. So the state of the thread of the program is stored in registers and in memory. The PC, or the program counter, points to what we need to do next. And the ALU is going to execute that unit. So so I think that the fetch and decode should probably be pretty explanatory. The execution unit should be pretty explanatory. For those of you that have had some other systems classes, what goes in what's an execution context? Because if we execute instructions, we have to modify some state. So what is in that execution context? Okay, that's on the right track. So register file, we need to change, like the state of the registers is very much part of the environment. The program counter is just a register, so we'll just think about that as a state of it. What did you mean by the memory bank? Yes. Uh-huh. Yes? Uh-huh. I see. So really, okay. So we have a machine, has a processor, it has some DRAM. We have to access values in DRAM at some address, and really, I think what you're getting at here is that usually this address is going to be a virtual address. So one thing that exists in the execution context of the processor is the mapping from these virtual addresses to the physical addresses of the DRAM itself, for example. So yes, so virtual memory mappings is another part of it. Part of virtual memory mappings is TLB state, permission levels in the operating system. Anything that the processor needs to have to define the environment in which we're going to execute an instruction. Could be exception state, other things like that as well. Exactly. Okay. So if I was to modify this diagram and say, I want to take this processor and I want to turn it into a superscalar processor, how would you modify my diagram? Yeah. Okay. So why do I need to have two fetch blocks? Well, if I'm going to execute two instructions at once, I better be able to figure out what two things I want to do. So yeah, so I am going to do that. So I'm going to change my orange box into two orange boxes. Am I done? I'm not done. Okay. Yeah, so I'm not going to say split because that implies that I'm making something smaller. Like if I want to execute two instructions at once, I need more resources, right? So I'm going to have twice as much fetch and decode, and I'm going to have twice as much execute capability. Am I going to split my execution context? No, because we're still processing the same instruction stream, which is one thread of control running within one context. So I'm going to do exactly what you said. And in this sequence of instructions now, if there happens to be independent ones, this fancier processor may identify that and sometimes be able to run two instructions per clock from the same instruction stream rather than one. Make sense? Okay. Now, that can be a problem because, like, for example, in this region of the program, no instruction level parallelism exists because I made up some instructions and I made sure that they were dependent. So this particular program in this phase could not take advantage of this type of parallelism because there was no parallelism to be had. Agreed? Okay, so I'm not really making this stuff up. If we go back to a very simple process, Pentium 4 from like a decade ago, and we look at their block diagrams, I can draw colors around their blocks, and you kind of see roughly the same structure. As you see that they had the ability to decode 3 instructions per clock, and they had the ability to execute 2 integer operations, a floating point operation, and a load operation all at once. So they had the maximum, so they could have ILP4 in some cases on this processor, and then of course all these results get retired into the register file, which holds the state. Then there's, I just wanted to point out, there's a lot of other stuff in this processor that's there to manage all of this fancy out-of-order execution, because at some point, if you execute things out of order, you need to make sure the results end up looking like they were in the original order. So you can imagine this can get kind of hard to orchestrate. You got to make this dependency graph, you have to respect the dependency graph, and so on and so on. So the point of this is that if you're a processor maker and you care about running a single instruction stream as fast as you possibly can, you're going to have a lot of stuff in that. You're going to have a lot of logic for dealing with ILP and out-of-order execution. If you've heard about some of these things, you might actually start to speculate on what the next instruction might do. So you might predict a conditional. You might predict a load and store. So there's all this stuff that's designed to help you out as a programmer, make your instruction stream run a lot faster. Another one would be the data cache. So what's the point of a data cache in a modern processor? Yeah. So yeah, and as we'll talk about soon, is that if you access memory, that's not one clock. That's a really long time away. And so a big data cache is, these are transistors that are holding data. These are transistors that are not being used to do computation. But it's worthwhile to burn these transistors. As the green line from last year went up, as we get more and more transistors, we can use a lot of them to reduce the cost of memory access. Now that's inefficient, right? Because if we had all the transistors being used for doing computation, that's kind of where we'd want to be. Okay, so now we're at major idea 1 in the class. And major idea 1 in the class is that all of this stuff that was being developed, whenever architects got the ability to add more transistors to the chip, their reaction was, let's figure out how to be more clever to make this instruction stream go faster. And what we're going to do is we're just going to remove all of that. We're going to say, screw it, it's gone. And so now we have all of this area on a chip that we can maybe use to do something else. And here's what we're going to do. We're just going to build another really simple processor in the same amount of space. So I took out all that stuff that was supposed to make a single instruction stream go fast. And I said, you know what? I'm going to make just 2 processors there. I'm going to make 2 processing cores. And each of these processing cores might be slower now. Let's say they might run 25% slower because they don't exploit ILP at all. They don't branch predict. They don't even have as big of a cache. But if I had a program that could run 2 instruction streams at once, I could actually run faster because I have 2 times 75% of the performance. I now have 1.5% times a faster performance on this workload. So if I run the program that I put up on the board, if I go back to this program, all the way back to this program right here, and I ran this C program on this processor right here, would it run faster or would it run slower? Why would it run slower? So if I compile that instruction stream with GCC, I get out a single-threaded program. I'm going to run that single program on one of these cores, which are 75% of the performance of my original core, and things got slower. So this is why, to some extent, why Intel was saying, well, that would be a really bad use of these resources. We have all this single-threaded programs out there. If we build these 2 simple processors, code's going to run slower. That's terrible. So what can we do about this? If you wanted to write a program that took advantage of this new processor, what could you maybe do? Yeah. Okay, and how would you actually, as a programmer, let's say in C, create 2 instruction streams? Okay, so one answer would be you could spawn a thread. You can spawn a P thread at the application level. You can spawn a kernel thread if you're thinking about it from the OS level. Exactly. So I did exactly that. So what does this program do? What does this program do? Yeah. It does. Actually, launches only 1 thread, just to be exactly specific. So how does it run? So I only launched 1 thread. It's close. I think you were on the right track. You had it right the first time. There's 2 threads of execution here, but where's the first one? Well, the first one's the main thread, right? So the main thread spawns a second thread, and then what happens? Well, the second thread I call sign X. So the P thread create runs my thread start. My thread start is here. So the spawn thread calls sign X. Notice that the original thread keeps going and also calls sign X. So that's where I got my 2 threads. So I did get 2 threads of parallelism, but I just wanted to clarify. So how did I distribute the work onto the original thread and the new thread? In half. So the original thread got the second half of the array, and the spawn thread got the first half of the array. Exactly. Yep. So now I have 2 threads. So that's great. And I can use this 2-core machine. because I have 2 threads of execution. They're actually both running essentially the same instruction stream. Those 2 cores can run completely in parallel. And even though they run each instruction stream maybe a little bit slower, overall, I'm doing better. So, and I wanted to point out that we will talk about in this class, especially starting next week, ways to sort of a little bit more expressively describe the parallelism. Like here's an example in a very fictitious language, where maybe I could just say, for every loop iteration, why don't I just tell the compiler, for every loop iteration, trust me, they are independent loop iterations. And so the compiler can kind of figure out what iterations to assign to various threads, or even how many threads to create. I recall that you suggested a slightly different mapping of the iterations to threads. You interleaved them. I did not. But both are different possible correct programs. And if I write the program this way, I could leave it up to the compiler, to the runtime, to choose how many threads it wants to use based on what computer it's running on. Because if I ran this program on a 4-core processor, I would have to change the program again to use all of those 4 cores. Whereas if we raise the level of abstraction up a little bit, I can now take advantage of this processor. Because it turns out that a lot of that fancy logic to run an instruction stream, run things out of order, these big data caches, they take up a lot of room on chip. And so if you start shrinking them down, you can get a surprisingly large number of cores. So here I've gone to 4 cores. Here I've gone to 16 cores. And I now have a new processor that has 16 cores and can simultaneously execute instructions from up to 16 instruction streams. So now I can run 16 threads all at the same time. And if you take a chip diagram these days, you can just kind of look at the various cores. So here is probably one of the more recent Intel chips that you can buy. It's the more recent than the one on my laptop. But you can just kind of see on the block diagram where those 4 cores are. And if you take a look at a GPU, it's basically the same thing. There's just, the things are a little bit, there's a few more cores. So here are the 20 cores on the GTX 1080s that are in the lab right now, the GPUs that are in the lab. And this is not, unique to desktop processors. They could be at the high end. There's Intel's 72-core chip, and you can kind of see all those one of the 72 cores there. The Apple A9 cores are not rectangular, and so on. So actually, is anything jumping out about these diagrams? Yeah. Still a lot of space that's not. I mean, not as much here in the Phi, but yeah. So what do you think? What do you think? What do you think this is? There's a lot of space on that chip that's not processor, and not even cache, because I actually went ahead and threw down where the L3 cache is. The L1 and L2 are in these blocks, so that part of that is L1 and L2. Does anybody know what this is? Yeah. Yeah. So this is all the graphics cores now on an Intel chip. Basically, a small version of a high-end GPU is actually located right here. Does anybody know? But this is a GPU, so even on the GPU, yeah. Yes, but they're not going to leave real estate open for dispersing heat. Yeah. Well, some of it is the interconnect, and actually we have an example where there's a full crossbar on the Sun Niagara chips. It's much bigger than the cores itself. In this case, no, it's not. I wouldn't expect anybody. This stuff is a lot of the fixed function stuff in graphics. So the fixed function texture hardware and stuff like that is still a pretty big piece of the pie in graphics. Here on the A9, up there at the top, you can kind of see 3 patterns. That is the Imagination Power VR GPU up there. So most of the die in all these mobile things is graphics, because you have these big, big high-resolution screens that are all very pixel. And then this is the L3, I believe. Most people, this is all speculation, reading from the websites and stuff. This is the shared L3. This is additional on-chip, I think DRAM, or just basically they're trying to put as much storage on chip as they can. Because as we'll talk about later in class, going off chip to read data from memory is very expensive in a mobile part. Okay. They don't? So this is this the, you don't think it is? It's certainly, well, they've definitely, this is probably SRAM then. This is probably like a couple megabytes of SRAM, scratch. Yeah. That's probably right. Great comments for somebody to come in. But that stuff's tiny up at the very top, actually. That's all on the GPU mostly. That's all those GPU cores, yeah. Anyways, someone that wants to go mine the internet to write the most detailed description up on any of these things, that would be a great comment. I mean, I'm actually serious. Somebody should go do it. Okay, so moving on. Okay, so here's another observation about the code. So the first observation about the code is that, well, every single, we can actually put different, the loop iterations are independent, so we can give them different processors. It's great. But it's a little bit more than that, right? It's not that the loop iterations are just independent. This is a for loop. All the iterations are doing exactly the same thing. They're just doing they're doing the exact same sequence of instructions, but they're doing it on different input data and producing different output data. So if you're an architect, you're like, wait a minute here. There's something new I can actually take advantage of, because architects like to be very, very efficient. So here's the second idea of the talk, is that we're observing that this body of the loop gets run over and over and over again with the same sequence of instructions on different data. So what I'm going to do is I'm going to take my little processor, and I'm not going to touch the orange box at all. But what I am going to do is I'm going to, instead of go from one ALU, I'm going to go to many ALUs. In this case, I went to 8. So the processor is now going to be able to decode one instruction and then apply that instruction to 8 different pieces of data. So I've just made a processor that's 8 times faster without the overhead of making 8 orange boxes. And you can imagine that the sophistication of processing an instruction stream and loading the instruction, and interpreting it, and doing all this stuff is quite a bit of overhead. So the extra cost of going to sharing an instruction stream across different ALUs is not as much as you would think. And this is a term that you'll often hear called SIMD processing, which stands for single instruction, multiple data. And video will have something slightly different, but I'll get to that in a second. So the same instruction is, from a single instruction stream, is fetched, but that instruction now operates on 8 different things in this case. So you can think about it like a vector instruction in some sense. So here was my program. Remember, our original compiled program had these loads and multiplies and adds, and they were all on one piece of data. They were scalar operations. When you saw mul R0 against R0, you had, well, take this 32-bit number, multiply it with this 32-bit number, and put the result here. Okay, so before, my instruction stream processed an array element at a time. And now what I'm going to do is I'm going to take that original compiled program, and I can be like, you know what, if I want to use these special new instructions that operate on 8 things at once, I can rewrite my C program. I can rewrite my C program to use these little macros that GCC knows that whenever I use this macro, like MMM256 load pack store, that I'm actually wanting to load 8 consecutive values from a memory address. Or if I want to have MM256 mul PS, that's actually saying I want to multiply these 8 values against these 8 values and put the result in an 8-valued register. Okay? So this is one way for me to take advantage of this new type of instruction set. And the compiler will take this C program and output code that looks like this. And notice that the instructions have actually changed. If you go obj jump and look at the binary, you will not see adds and multiplies on the standard x86 registers. You will see adds and multiplies, the vmul version of it, which is vector multiply pack scalar, which is, so treat these inputs as contiguous vectors of 32-bit ints, or 32-bit floats. And this will be the result. And this program cannot run on a processor that doesn't support these 8-wide vector instructions. It will segfault with an invalid opcode. So I'm showing you the AVX2 versions of these opcodes. Batch, single precision, sorry, yeah. Thanks. You're right. Pack single, not pack. Yeah, so there's a vmol PD for the double precision as well. Okay, so how many people have written code like this? Randy has. I have. A few people in the audience. And you're more than welcome to in the extra credit in assignment 1. Why not let the compiler do this for you? It can, sometimes. But the state of the art in modern compilers is to take this program written like this and analyze the code to figure out when it's possible to basically replicate that for loop. It's still pretty primitive. You will not be particularly happy with the results that you get out of a modern optimizing compiler. But note that, but if I go back to this program right here, notice that just by declaring that every iteration is independent, I've actually told the system that not that you can create as many threads as you want, but I've actually told the compiler, feel free to vectorize this loop as well. So I'm actually giving it the signal to say, look, you can try and do vectorization to get the SIMD behavior as well as get the parallel multi-core behavior. Okay. So now I have this processor that still has 16 cores, just like the last time I threw this diagram up there. But now every one of those cores has 8 ALUs, and each one of the instruction streams running on those cores are processing 8 wide vector instructions. So even though I'm still only running 16 simultaneous instruction streams, I am driving 128 ALUs, and I'm effectively running 128 iterations of my sinx for loop simultaneously and in parallel. So this program would be 128 times faster than a single simple core that only had one yellow dot and one orange box. And yeah, so I guess I jumped ahead of myself, because I just wanted to point out that just by telling the compiler that all of these loops are independent, you're starting to give your tools information that might allow them to generate these vector instructions for you. Okay, so here is a question. So the way to leverage all of this really high throughput computing, what was the key insight? What allowed me to pack this processor full of 8 ALUs and only make one orange box? What was the key insight? Let me go there, yeah. That the multiple iterations through the loop, or multiple things I need to process, can be processed with the same instruction stream. Right? That was the observation. That was the key insight. But now I wrote this piece of code here, which I just made up. So imagine that this is being run in a loop. This is just the body of the loop. And so I'm going to load a sub I. My loop iteration is I. And I load it into a local variable, and then I'm actually going to condition on it. I'm going to say, if the input value is greater than 0, we're going to run this block of code. Else, we're going to run this block of code. So this is normal C code, right? Nothing fancy here. So there seems to be a conflict. Can I run this code on the processor, the SIMD processor that I've so far designed? Yes. So let's assume that I only have one core for right now. Let's not think about the multi-core part of this. We have one core. It has 8 wide SIMD behavior, and I want to run 8 iterations of this loop with this conditional code on that processor. Can I do it? Can I not do it? Should I give up? A bit mess. What do you mean by that? Okay, so let me draw this out. Let's get to that point. So first of all, before we get to the if statement, everything's great. All the iterations of the loop need the same instructions. All of them have to evaluate the loop predicate. They have to evaluate, is x sub I, x greater than 0? So we're running along, and I'm visualizing this by saying, what is every ALU doing per unit time. So time is going down, and horizontally are the various ALUs. So notice that they're working on different data. So when they all evaluate the loop predicate, they're going to end up with different results, right? So I'm illustrating that here by saying, okay, for these ALUs, they're working on iterations where it's true. These ALUs, we're working on iterations that are false. So now we're getting to the problem, because now we know that 3 of the iterations need to take the if branch, and 5 of the iterations need to take the else. And so you were starting to allude to a bit mask. And now, in light of this diagram, what did you mean by that? Okay. So what's going to happen next? Let me put it that way. Is that currently the first 3 steps of this diagram, I've said that all the units, all 8 units, are doing the work. They're doing work, and they all at one point the result of this last instruction is true, false, true, true, false, true, false, false, false. What's going to happen on the next instruction? In fact, which instruction are we even executing at this point? Because we cannot execute different instructions for all the different columns, right? Because the processor just can't do that. Yeah. Okay, so what you're saying is, well, we have to execute the if block for 5 of those, no, for 3 of the iterations. So let's go ahead and do it. Let's go ahead and execute the if block. And let's just be careful to just effectively not do anything here. We can execute the instruction and throw away the results, or we can maybe just turn off the ALU. These are all implementation details. But the point is you can think about it as, well, if a column doesn't actually need the instruction that's being executed, it just turns itself off. Or its result is masked off so that nothing ever happens to the register. And then can someone explain to me why the X is moved in the second half of this diagram? Yeah. Because the processor had to execute the else as well for some of the lanes of this vector, right? So that's exactly what happened. And then what happens at this point when we finish the else? We're not done. There's more program. We're going to resume the additional code. The annoying bit, but I like to be precise. What is annoying? Annoying is not a technical term. Yes. Okay. Oh, what about branch prediction and how this can mess with this? Correct. Well, I actually, at the risk of making a mistake, I don't actually see how this is inconsistent with branch prediction. Because branch prediction says that I believe that this is the true-false outcome, which means that I believe that this is the instruction that I need to do next. Any reason why I cannot do that at either the granularity of vectors or at the granularity of the individual lanes, and I absolutely need to squash the result if I mispredicted incorrectly. So if I get halfway through this block, and then the prediction result comes through, and I realize that the mask that I had set is not consistent with reality, I can just squash and move back up and start over again. So I think you could design a branch predictor that worked in the context of these vectors. So one way you can think about it is everything that you used to do on a single lane, you now need to reason about 8 of them. So you probably need to take worst case. Yes, sir? Oh, I just made that up because that's the outcome of the program. So imagine that a sub I is less than 0 or greater than 0 for iteration 0, 1, and 3. And imagine that the input data from memory is greater. Yeah, that's just like the case that we're working on. Yeah. Yeah. That is how the hardware is built. because the hardware decodes one instruction and says, all 8 of you need to do an add.
Right.
That's the only way it works.
So in this situation,
Uh-huh.
how are you chaining or throwing away these chains?
So I could say, we can describe several implementations, of which you will make one of them on assignment 1. But if you want to think like a software architect, maybe you say, I'm going to do all the work, and then I'm just going to avoid the write to the final register. So imagine you had a special, like if we don't think vector, imagine you had a special a modifier on every instruction, which has an extra bit on it. So add R0, R1 into R2, and it has an extra bit which says actually do the work and skip the write. That's one implementation. Another implementation could be nothing happens at all. All of the circuitry is turned off because we want to save the energy and not burn the energy on results that we want to get rid of. Yep. I don't see any reason why I could not. I have to respect the program dependencies, but I absolutely can have out-of-order execution. For example, there could be ILP within any one of these blocks. This didn't make it any harder that out-of-order execution needs to respect a conditional dependency in that. We had that before if we had an if statement in a program. So yes. So you're assuming that that needs to be done in software with additional instructions. But if you built a chip like this, you would almost certainly have an instruction that was like a single cycle is all on or any on and stuff like that. Or this operation, x is greater than 0, is a vector operation, right? And the results of that vector operation is a bit mask of 8 bits. So all I need is an instruction to say are all bits 0 or all bits 1 to know if I need to go into the else of the if block. So it's actually no. There's not as much overhead as you think, but there is some overhead of managing the aggregate instruction stream, and that's actually absolutely true. Yes. That raise like an exception or a floating point error, something like that. Yeah. Now, so that's a great question. Like for example, if this created a divide by 0 because it was junk, yeah. So you should think about it as really squashed, as in it's not executing and generating any kind of exception or anything like that. And if it does, then the semantics of that need to be really well defined. And exactly how that's defined in x86, I could not tell you off the top of my head. It's a really good question. Yeah, I'm not exactly sure what happens when you do a masked divide by 0 on x86. I'm sure it does not generate the trap, or I would hope it doesn't generate the trap. It would be hard to deal with if it did. Okay, so I just wanted to point out that after the branch, we are again going back and running at full rate. So first of all, at this point, we're running at 8x speed. At this point, what is our efficiency? 5 out of 8, right? At this point, what's our efficiency? 3 out of 8. Okay, so can someone come up with a worst case piece of code for this type of processor? How do I, first of all, what is the worst case in terms of throughput? 1/8. So the worst case scenario is you have one of these really nice processors that can do 8 things at once, and for most of your code, it's only doing one thing. Can somebody hypothesize a piece of C code or a piece of code that when run on a bunch of iterations at once could cause a bad problem? Yeah. So if I have a case statement, I need to go 8 different directions. Yes, that could work. There's even simpler solutions, actually. But that's absolutely correct. Yes? Print every number in order. So yeah, so that would be completely sequential code that couldn't take advantage of this processor. But imagine like think of a loop body, like a loop body that can run on every iteration completely in parallel. And I just showed you how to lose some performance if there's a conditional. What's the simplest condition if-else statement that you can write that can really kill you? Yeah. Okay, but let's assume that all the loop iterations are independent and they should be able to run in parallel. So the only thing that's slowing us down is the inability to share the instructions across them. Absolutely, we can make a program that's not parallel. Yep. Exactly. So the answer would be, if condition, run for 1,000,000 cycles, else run for 1 cycle, and you want one of the 8 iterations to go down the thing that takes forever. So that most of the time, you don't have to nest your ifs, and you don't actually need 8 different cases. You can just say, look, I'm going to send one person down something that takes a lot of time, and the rest of the guys are going to run at 7/8 efficiency on something that doesn't take very much time at all. Exactly. Okay. So very good. So there's some terminology that you can review after lecture a little bit, but we often say that an instruction stream or a program has coherent execution when all of the iterations of a loop can use the same instruction stream. And we often use the term to say that the instruction stream is divergent when it is not coherent, meaning that different iterations of the loop, because of conditional control flow and branching, can no longer share the same instruction stream. So a divergent instruction stream will suffer in performance on a SIMD processor. And that there's sort of a couple of ways that SIMD shows up in modern machines. So the most obvious way, and the way that you'd be exposed to it on an Intel processor, is that the compiler will generate new, completely different instructions that say these process 4 pieces of data. And that's like an SSE instruction. Or with AVX or AVX2, these are instructions that process 8 pieces of data at a time. And then there's this emerging AVX512 that's coming out next year, where these processors will process 16 pieces of data at the same time. So at this point, it's the programmer writes a program, and either the programmer says explicitly use these instructions, like that messy code I showed you, or the compiler chooses to emit these vector instructions. That's how it works on x86 CPUs. That's often called explicit SIMD. On GPUs, it actually works a little bit differently. And this is a little detail, and you guys can worry about this later. But the way it actually works is that if you look at a binary on a GPU, it actually is a sequential set of instructions. It's a scalar set of instructions. So it looks just like a non-vectorized binary. But the GPU program will run that on 8 pieces of data for you at all times. So it's sort of implicitly done by the hardware for you. And the implications of this are a little subtle. But on most CPUs these days, the vector width, the amount of SIMD, is about 4 to maybe 16. On GPUs, it tends to be about 32 to 64 for high-end GPUs. So you can imagine that if you have divergent code and you're running at 1/64th the peak of a machine, you're going to be like, wow, I'm really far off what I should be actually expecting. So just to give you some examples of some real-world processors, or some cartoons of some real-world processors. So this is the Xeon E5 that you have in Gates 5 that assignment 1 is being done on. 8 cores, 8 wide vector ALUs. And at least, just to oversimplify things a little bit, we can do 1 multiply-add instruction on those 8 ALUs per clock. So if you add it all up, if you add 8 times 8 times 2 for a multiply-add times the clock rate of 3.2 gigahertz, you get for about half a teraflop of performance at that clock rate. And that's at 140 watts. If I wanted to take the exact same cartoon and apply it to a modern GPU, like the GPUs that are in the exact same machines, we could take like the 1080, where there are 20 of these processing blocks, 20 of these cores, which NVIDIA likes to call SMs, and they have groups of 4 32-wide vector ALUs. So they can run 4 instructions per clock, and each of those is a 32-wide instruction. So same concept, just slightly different geometry. OK, so that was the parallel part of this lecture. So we talked about we can just take all the stuff out that was useful for running a single instruction stream fast. And if we have parallel programs, we're better off making all these simple processing cores. And even moreover, if we have parallel programs that have loops where they do all the same instructions, we can make an even faster processor by replicating only the ALUs and keeping everything else the same, sharing everything else across the ALUs. And now I want to get to close up on this question about, wait a minute, you're not talking about memory at all. And last time, you said that communication and memory traffic was the most important thing in any parallel program. And so that's what I want to get to right now. So I want to introduce two terms. What is latency? What is latency? What does it mean? If I say the latency of a memory operation is this many nanoseconds, or if I said the latency of the amount of time it takes you to get an answer on Piazza is 3 minutes, what is latency? Yeah. It's a unit of time. It's how long it takes for an operation to complete. If I ask for a value for memory, how long does it take for it to get back? If I ask a question on Piazza, how long does it take for a TA to respond? What is bandwidth? What is bandwidth? Yes. So if latency is an amount of time, bandwidth is a rate. So bandwidth, we care about how many bits per second go over a wire, or how many instructions per second a core can access. So if I walk all the way across the room, and let's say I wanted to, let's say I wanted to carry a bunch of stuff from one side of the room to the other. If I wanted to decrease the latency of the operation of getting my bag to the other side of the room, what should I do? I should run, right? I should run across the room, and I should get it there faster. Now, if I wanted to increase the throughput of me getting stuff across the room, imagine I have a whole pile of bags. What could I do? I carry more bags. I'd probably call a bunch of TAs. Now, does running faster across the room and coming back, does that help my throughput? Why not? So there's a little bit of a relationship between the two, and we'll talk about it more, right? So if I ran really fast and I got back, that's like increasing instructions per second by decreasing the amount of time it takes to do every one instruction. But in general, when we want to talk about throughput, we're going to get more throughput, not necessarily by running, but by carrying a bunch of bags or grabbing a whole bunch of us to walk across the room at once, right? So, what? Well, that would maybe decrease latency, but it wouldn't necessarily increase throughput. No, it would probably increase throughput too. Okay, so I just wanted to be very clear about these two terms. We have memory latency, the amount of time it takes to read data from memory. That could be cycles, it could be milliseconds, nanoseconds, and bandwidth, which is the rate at which information gets traveled over a link. So far, we have not thought at all about not being able to run an instruction because we were waiting on something. And now I want you to think about that. So when a processor executes a load instruction from memory, the machine, the computer, has to go get that data from memory and bring it to the processor. And that can take a long amount of time. And that memory access times in modern computers are on the order of hundreds of cycles. So even though I said my processor can do an instruction every clock, if every other instruction is a memory access, then if I execute this load and this load, it might be 100 cycles before this add can actually happen. So that processor is just sitting there twiddling its thumbs, not doing a darn thing, for 100 cycles in order to do a single cycle math operation. So we were concerned about running at 1/8 the rate just a second ago. And now I'm telling you that we could be running at 1/500th the rate if we're always waiting on memory. So this is kind of a big thing. So given what you've learned so far, like in 213, how do processor designs avoid waiting for hundreds of cycles to get data from memory? Yeah, caches. And so what do caches do? Do caches increase or decrease throughput? Do they decrease latency? What do they do? They primarily serve to decrease latency. Now, people watching around the internet are going to say, well, they also increase throughput too, and that's true. But we'll talk about that later. But the primary purpose of a cache is to decrease the latency of memory access. And what did I tell you at the beginning of this lecture that I did to make this processor with a bunch of cores? I threw out, or at least made it a lot smaller. So the primary thing that I decided to do was take out this big honkin' cache, like a big L3 cache, that's meant to absorb all of these memory accesses and get them back to the processor really quickly. So, and which is the whole point of that cache was to reduce stalls by reducing memory access latency. So one thing that many modern CPUs do as an alternative to caching, as you mentioned branch prediction earlier, they can also do prefetching, which is saying, I think I'm going to be accessing this address in the future. Well, I'm going to go ahead and issue that access now so that whenever I get around to actually needing it, it is in return for memory. So prefetching is one interesting example of exploiting a little bit of instruction level parallelism, and that all of these instructions in the meantime can be executed out of order by moving this memory access way up here. But again, this is more smarts to the processor. And the theme of this lecture is I do not want smarts in the processor. I want simple, dumb processors. And I want to pack them full of ALUs because ALUs actually do math. So anybody have any ideas on what we can do? Because I'm saying I don't really want one of these prefetchers, and I don't have the budget anymore for a big cache. Am I out of luck? Did I just make a bad design? So imagine that you're doing your laundry in Morwood. So if you put your laundry in, how long does it take? Yeah, so let's just say it's just the washer. So it takes 45 minutes before action is required. How many of you sit there and watch it? How many? So what do you do instead? You do something else. You do something else, and clearly that something else is not dependent on your laundry finishing, because there's no dependency there, right? So there's some parallelism in the task that you have to do that day. And your philosophy is, if there's something that I'm waiting on finishing that somebody else or some other unit or some other piece of machinery is supposed to do, rather than sit there and wait for it, I'm going to go do something else. And that's exactly what we're going to do in most modern throughput processors. So we're going to take a technique, which is often in architecture called hardware multi-threading. And the big idea is just, we're going to go do something else while we're waiting. So I'm going to take that core from the previous slide, one fetch and decode unit, same ALUs, one execution context. And what I'm going to do is I'm not going to change anything at all in the core, but I'm going to go from that one execution context, I'm going to go to 4 execution contexts now. So all I did was replicate state. So now my processor has on it the ability to maintain 4 different sets of register files, 4 different program counters, 4 different virtual memory mappings, whatever you needed to run that instruction stream. And then what the system is going to do is, let's just say we're running, again, time is going vertical, just like the previous diagram, and we're running a thread that's issuing 8 wide vector instructions, and it's just doing its thing, and it's going to running at full tilt, going down the slide, and at some point, it issues one of those loads. Boom, I need to load this data. It's not in cache, missed my tiny little cache. It will not be back for 100 cycles. So either that processor can sit there and wait, or it can choose to start running instructions from another thread that it has just sitting off to the side. Right? So it immediately switches over, starts executing instructions from another thread. And then when that thread stalls, it goes to another thread, and so on and so on. And notice that at some point, whenever my 4th thread stalls, if I kind of walk back across here, well, that first thread has already become runnable again. The 100 cycles has passed. So I can just begin to pick up. As soon as the processor goes idle, it can pick up back with thread 0 again, or some other thread that's runnable. And notice now that what is the utilization of my processor in this example? Sorry? It's 100%. And how did you guys figure out it was 100%? There's a lot of white space in this diagram, so that's kind of concerning to me. Yeah. Exactly. So in other ways, if I look at any horizontal line across this diagram, I'm going to hit blue at any point, which means that there's some thread always running on the processor. And that means that my ALUs are always doing something every cycle. And if my ALUs are doing something every cycle, there's no more processing to be had. I'm using all my resources all the time. Now, what is the cost of this technique? Yeah. I have to context switch. I told you I actually added more resources to my processor to make that really, really cheap. Like, just think about it as 4 register files, and the processor just starts using the other register file. So let's say that there's 0 time spent context switch, unlike an operating system. Yeah. Yes. So there could be some interesting effects that they're going to miss the cache even more. Who cares? Whenever they miss the cache, I can go do something else now. Yeah. Well, so I definitely paid the cost of saying, look, now, I said I didn't want the cache, but now I'm using some space for the execution context, which is a little bit. But I also like you said about how they were competing for the same resource. So how long would thread 1 have taken to finish its work if this was not a multi-threaded processor? Would it have finished earlier or later than this point? Earlier, it would have started here, right? It would have started running again here as soon as that data was back, and it would have finished by about now. So I pushed this even farther. Remember at the beginning of the lecture, I made more slower cores? Now I'm actually sharing those slower cores amongst more and more threads. So this is a major idea of throughput computing, is that any one thing is taking longer to actually finish. Because I don't care about the latency of finishing any one loop iteration. What I care about is finishing the entire million iterations in the lowest amount of time possible. So I want to maximize the use of my resources to gain the highest throughput. So, now I just want to point out, as you guys were starting to allude to, well, you can think about having a finite amount of execution context, right? A storage. And if I have one thread, it might have a lot of storage. So it might hit in the cache a lot, or there might be a lot of registers that I could use. I could go the other direction and divide this chip into 16 different threads worth of storage and say that every thread gets a very small number of registers or something like that. Or I could pick some middle ground in between. So I just wanted to, so this is the last idea. And so notice that this last idea was not about adding resources to adding execution resources to the processor. The first 2 ideas were more cores, more ALUs per core. The last idea was actually adding more state so we could use the existing resources more efficiently. Okay. So I'm going to jump through this, and I want to just kind of summarize here. So I've made this fictitious chip over this lecture, right? So my fictitious chip has 16 cores. It can process 16 instruction streams at any one time simultaneously. Those instruction streams can execute 8-wide vector instructions, SIMD instructions. And my processing cores actually can interleave 4 instruction streams, 4 threads per core. So at any one time, I can have 64 threads live on the processor, but I'm only ever running 16 of them at once. And so that means that I need 64 times 8, 512 loop iterations to actually fill up the whole machine. So if I'm running a for loop that doesn't have 512 iterations, I don't have a big enough problem for this computer. And a GPU, so this is kind of very CPU looking. A GPU is just all the same ideas kind of pushed out to an extreme scale. So if Intel says we don't want to give up that much cache, or we don't want to give up that smart of a branch predictor, we want to be able to carve off a little bit of space to run single-threaded programs pretty fast still, but we'd like you to be able to run 4 or 8 of them all at once. The GPU guys are saying we care about graphics and deep learning and machine learning. We don't care how fast any one instruction stream goes. We want to maximize throughput. And if you make that completely different design decision, you start ending up with a processing core that looks like this. So this is the GTX 1080 in your lab. And what it has, first of all, it has support for not 2 or 4 threads per core. It will actually hardware interleave 64 threads per core. And at any one clock, it will choose 4 out of those 64 threads to run, and will execute one vector, 32-wide vector instruction for 4 of those threads. So if we go back to my definitions, which I skipped over a little bit, there's 2 types of multi-threading going on. There's simultaneous multi-threading, which means there are indeed 4 threads running on a core at the same time. There are 4 sets of execution units. There are 4 threads running. There's also interleave multi-threading, which is what I diagrammed for you. Out of the 64 threads that the chip can support, it will pick 4 of those 64 to run in these 4 blocks at any one clock. And then the instructions that a thread runs are 32-wide parallel vector SIMD instructions. Same ideas, nothing new. And then there are 20 of these cores to get to this diagram. And if you're wondering, yes, I did have to rasterize these images for Keynote to actually render the slide. So there are 20-some cores on these GPUs. And so what the cost of this type of getting this type of performance is that if I multiply 20 times 64 times 32, so there's 2,000 elements of data, 2,000 loop iterations are necessary to use one of these cores, and I have 20 of them. So if that parallel for loop that I was using in my SignX program doesn't have on the order of 40 to 50,000 loop iterations, you will not use this processor very effectively. So the scales are just much, much larger. Okay. So last 2 slides, and we'll get out of here. Notice that there's a big difference in how the CPU architects have designed their cores with the same principles, just different numbers, than what the GPU architects have designed their cores. And it's not surprising that that actually changes how the memory system was laid out as well. So CPU cores have these big caches. They have a 32 kilobyte L1 or smaller. They have like a 20 megabyte L3, such as the L3 cache in the Gates 5 machines, because these cores only have 2 threads to hide latency. So they better not miss the cache very much. These GPU cores have 64 threads to hide all that latency. So they assume that they're going to miss the cache, because first of all, the amount of cache per thread is low. And second, they build a tiny little cache and a huge honking memory system that provides 300 gigabytes per second of bandwidth. So this whole chip is engineered for maximum throughput, assuming that a much smaller number of data accesses actually hit in the cache. Yes? This is much more expensive RAM, basically, to sustain the 320. Basically, in general, in computer science, if things are expensive, you can't have very much. But OK, so here I want to close on this thought experiment. Here is a problem that I want you guys to think about running. This is your standard NumArray or MATLAB program, right? I have 2 vectors, A and B. Vectors A and B, let's say, are huge. Let's say there are many millions of elements. They don't fit in cache. And I just want to perform this simple computation of multiply A times B, store the result in C. Every element. Multiplication. 1 second. Or it was a question about the problem setup? That was just element-wise multiplying. So not a dot product officially either, because I'm not reducing across the dimensions. This is the simplest possible computation. Element-wise multiply A times B. OK. So who thinks that this is an excellent computation to run on a modern parallel processor like that big honkin' GPU or even the CPU that I just showed you? So who would vote to say that this is an excellent computation for this processor? Is it parallel? Can it share an instruction stream? OK. OK, so not everybody raised their hand, though. So I'm a little confused. So what about everybody else that does not believe that this is a good solution for one of these processors? Yeah. So that was a complete factual statement. So what are you getting at? Okay, so you said it takes a long time to load the data, and then you said bandwidth. So when you said that takes a long time to load the data, I thought you were going to say, well, you're going to be bottlenecked by the memory latency that you talked about. But then I was going to say, but I have all these threads. So let's assume that that threading hides all of the latency. But then you said something about bandwidth. And then I started to agree with you more. So do you want to clarify your statement? Okay, good. So you made a throughput argument. And that's exactly what's going on here. This is about the worst possible thing you can do on any modern computer. And the reason why this is about the worst possible thing you can do on any modern parallel computer is let's just do the math. Like you said, this computation loads two elements from memory and loads one for every math operation it does, which means it needs 12 bytes of bandwidth for every instruction that we can execute. If I just do the math of having 2,500 multipliers on my chip times 1.6 gigahertz, if I do the math, I would need about 45 terabytes of bandwidth to actually keep the chip busy. I don't have 45 terabytes of bandwidth. If you remember back here, I actually have an amount of bandwidth, but it's only 320 gigabytes. Delivering 45 terabytes of bandwidth to a processor is yet to be done. So if you do the math of dividing 320 gigabytes by over 45 terabytes, this GPU will be running about 1% of the time. You could actually take out 99% of the ALUs. You could divide 2,560 by 99, and that's how many ALUs you could put in the processor, and you would run at exactly the same speed. And if we did the same calculations on an Intel CPU, we're in the same ballpark, about 3% of the total performance available to you. So it absolutely means that most programs you will write, the trick is how are you going to reuse that data and fit in the small caches that you have. Otherwise, you will not be able to use these types of computing resources. So anyways, I will stop there. I have on the slide deck a bunch of other slides that I never intended to cover in lecture, but are good fodder for review or comments that people have asked questions about in the past. And I have some diagrams for multi-threading, which can be really helpful, I think. So.
So when one thread take over the processor, I think because fetching the data and do the execution are using different part of the processor.
Yes.
So that means fetching the data, all of the ARU are in idle.
No, it's all pipeline. So the ALUs are working on the previous instruction while the instruction fetches decoding the next instruction.
Okay, because I'm thinking like maybe like if it is fetching data for one of the thread, the ARU can do the work for another thread at the same time.
Yeah.
So then like the thread take over the entire process.
Yeah. So it is absolutely true that all of this is pipeline.
Okay.
So if these are my three, I'm still on my mic.